All right, so the topic of today is going to be sunlight parametrics. So what we've done over travel week and what you guys have been doing in your labs is been looking at basically ways of incorporating logic into your scripts. And we did this with the week 8 materials where we're looking at logical statements. So we're asking basically like a question that's like a true-false question, okay? And that's going to be the basis of some of the algorithms that we're going to be looking at this week and probably for the rest of the year. It's a really important idea in computation that you're creating logical flows. So a lot of the times the programs that we've been working with have been flowing in one direction. They go from input to output. When you introduce logic, the programs can begin to branch, right? You can say like it's either going to go in one direction or it's going to go in another direction or it's going to go in any number of different directions. That's been a big change, okay? Instead of one kind of output, we might have a completely different output depending upon the kinds of conditions that we set up, okay? Today what I'm going to do is I'm going to start to build on the idea of logic, build on the idea of attractors that we looked at in week 9. So an attractor is what? Can somebody kind of explain to me what that is? Like what that algorithm is? Anybody? Rob, what's an attractor? Yeah.
An attractor?
Yeah, what's an attractor?
Something that attracts other components, or I'm not really sure.
Somebody help him out. What is it? How does it work? I guess I should say instead of trying to define it that way.
It's
How does
gathering certain information around a point? So
Okay.
cutouts or
Okay, so you have a point, and what is kind of gathering or what's actually happening there? You have a point, and it's being measured against what? What's the comparison being made to in the script? We have a distance component in a lot of cases, right? So it's the distance between the point and what? Other points. Yeah, it's actually not that difficult. Okay, and we get a distance. So there's a distance from every single point to that point, and we get a number, basically a distance. Okay, and we use those numbers that are attached to each of those points to do what? What are the kinds of things that we did? You just said it there.
so you kind of play with the distance between two of them, the different forces between them. We were playing with magnets almost.
Okay, but I mean, what kinds of effects does it actually generate? Maybe I need to jog your memory visually. Okay, so this is what we're talking about. Okay, so you said it kind of works like a magnet, it's kind of attracting these. What's actually happening here? In a very, very simple formal way. We have a number that we get from the distance of the point to the other points. What do we do with those numbers? What do we see?
Circle sizes.
Yeah, the radius changes, right? Now, we have to manipulate that because we just get this raw number that's almost kind of an arbitrary, number. And this is why we have other things we have to actually take this and actually divide it by some number. We have to set a minimum component because we want to set a normalizing size. If we don't, it just becomes basically those numbers are too arbitrary. They just get very large. They just kind of blow this thing up. Maybe that looks interesting. But it certainly doesn't create these kinds of effects that we're talking about. We had another thing we did in the lab where, so this is the effect, right? If we have less distance between the point and the other points, we have a smaller radius. It's a one-to-one relationship. We did a modification where we subtracted that from some number, and then actually gave it so that they made this larger when it's near here. Okay, so two very, very basic effects. But I hope that, in the examples I showed during the lecture, and as you start to look at some architecture, you'll see that this is actually kind of a very common effect that architects are using, right? And this is sort of evidence of a very simple form of computation. It's only one kind of relationship, okay? What the idea is that these points can represent different things in your design. They could be the location of a tree. They could be the location of a light. If you guys recall, in the example I showed you at the end of the video, where they were looking at where the sprinkler heads were and where the lights were, and they wanted there to be less openings where those things were because they wanted that to be the sprinkler head or the light. Okay, and so this is kind of an abstract example, But when you have an intention behind this in your design, right? This is where this starts to become. You're starting to program the form of your design. Okay. So, but again, very simple algorithm. Like it's just measuring the distance. But there's a myriad of applications for it. These are the kinds of things that I was looking at. So this is this museum, using it to filter in light. Let me kind of skip through here. It doesn't just have to be openings. It could be, it could be a different kind of opening where these things begin to kind of peel, upward as opposed to just a regular opening. Shows you how to get points along a line. So it doesn't have to be 1 or 2 points. You can actually distribute points along a line and use that. So you could draw a shape and have that. Change the openings in your building. You could use an attractor. We talked about pushing and pulling things. What's actually happening here, like mathematically? Okay, somebody explain. Like when I have this part of the surface being pulled up, this part of the surface being pulled down. What's the parameter that's actually changing? Here. Before it was the radius. What's the parameter here? When something moves up and down, like what's changing? The z, the z value. The displacement's fine, but it's just a simple, this is a flat sheet of points, I can use the attractor logic and I can say, okay, where it's near a point, reduce the z, right? Or where it's near a point, increase the z, okay? And that's just a very, very simple way of thinking about how to disturb the surface. Again, you could be designing a park or something, you want there to be mounds wherever there's a tree, the positions of the trees are going to change, or the positions of the trees are going to be distributed by some other logic. This is going to help you shape your topo like lickety-split, okay? And as you change those things in the project, the topo changes automatically. So this is an example. And actually, in this case, it's both, it moves both the surface, and you can see the attractor logic in the form of the rectangles in this design. Okay. And you can actually, if you get into Revit, and make a plea here, I think I told you guys this before, but there are attractor scripts, there are attractor components and things like this. This is something that actually can be applied parametrically in other software. It's a very general idea. Okay, we saw some other examples of this. I'll kind of skip through these, but so rotation. So this is where we're going to begin today. So I showed you guys attractors. They didn't really give you, other than kind of just really formal expressive things, they weren't actually tied to any kind of phenomena or any kind of intent. So what I'm going to talk about today is daylighting. And actually, I'm actually talking about sunlight, not daylight. Sunlight is not daylight. So light, daylight, if we go back to the rendering lecture from before break, we talked about how we simulate light in a space by physically simulating the bouncing of photons in a space, okay? That's really what we consider daylight, okay? Daylight's what you go into Dale's lab and you sort of put your model inside of his sun dome and you take a photograph of it, okay? It's a scattering of light. It's both direct light and indirect light. It's the quality of light that you get, okay? We can simulate that parametrically in other software, through making renderings, but also through tools like Vasari and through different tools like that. But in Grasshopper and in Rhino, sunlight. We can simulate the sun angle. Well, we can't simulate the scattering of things, but the sun angle is still kind of useful. It's not the same as thinking about the intensity of light or how hot it makes things. But if you're staring directly at the sun, for instance, right, it's got a whole bunch of glare. If you have workstations, you don't want that sunlight directly sitting on top of your workstation throughout the day. Okay. We want to shade that. We want to prevent that from happening. So that's one thing that we can do parametrically in Grasshopper. And I'm using this as the basis of the lecture today to start to say, this is one kind of information that we can model parametrically, and we can use it to change the form of our building. Okay, and it's actually just based on angle. So before we looked at the attractor point and the proximity of the point. Now we're going to be looking at a simple idea, and that's that we have the angle between a point and another point, and we're going to use that to drive different scripts. And in this case, this point is the sun, which we can track pretty much mathematically, right? And the other points are places in your building. Okay? So there's going to be a little extension of that idea. If you want to be able to study daylight, you're going to have to look at some other tools, but it's definitely possible. So again, the ideas of sunlight is to prevent sunlight where people can't move away from it. Okay. So for instance, like if this was your desk, like you'd be a pretty unhappy person for a few hours a day. Right? You would want to get away from that. You don't want that light in your conference room, just totally blasting the place. You don't want that light, bouncing off this building and like superheating your Jaguar. Did you guys see that story in London, right? The melting a Jaguar. It causes heat and causes glare. So this is one thing that I want to talk about today. When you get into simulation software, a lot of it is just basically tracking these kind of sun angles. And here they're actually tracking the multiplicity of angles to see where they're going to hit this other building. Okay. That actually is Charlotte right there. So these are from the daylighting lab. Okay. How many of you guys have had daylighting before? Here's study. Alex. Okay. So you're going to correct me whenever I say something wrong. Okay. So it's not my field of study, but I know enough to get myself in trouble. Okay. So sunlighting works. It's completely dependent upon where you are on the planet, obviously, because it's going to change the angle of the sun. Okay. Typically, the sun, in the northern hemisphere, right, travels to the south of us. You can see this is a bunch of sun paths. We have the sun here, in January. You can see it's very low in the sky. The sun here in September, when you get into like the equinox, it's kind of in the middle, right? And then it gets kind of shallow and low, and then it gets kind of sharp and high during the year, and it kind of oscillates between those, and you get these kind of sun charts. And what's useful about this is that if we have these angles and we know where the sun's going to set, we know where the sun's going to rise, we know where the sun's going to be, we can essentially draw this curve in 3 dimensions. And then we can input where the sun is at a certain time, and that'll give us that like point where the sun is. Okay. Then this is what it looks like in 3D. This might be a bit more helpful. Okay. So you can see like in the longest time of the year, longest day of the year, June 21st, right? You can see that the sun, it's actually way back here. Actually, in this particular example, starts kind of in the north, and it goes up very high. It traces a very long arc. The sun's up in the sky for a very long time, right? And you get to September, it's much more down, to the south. It's got a much shallower arc. That's the shortest day of the year, right? So it's kind of a graphic explanation. We're using the sun's path to explain, why the days are longer, why the days are shorter. I don't know if you guys have ever seen something like this before, but this is essentially what we're going to try to construct parametrically. Okay, so this actually brings up another interesting point. There may be some tool out there, like now, that actually does this. Like there may be some magical Grasshopper thing that I just plug numbers into and it gives me this curve. But at the time when I made this, I was doing a project and I didn't have this. Okay, and so I had to actually make a tool that would do this. Okay, so I had to study how the sun works, how to find this information, and essentially construct a tool for myself that would give me this information so that I could continue to do the other thing I wanted to do. So I needed some computation so I could use my computation. Okay, and this is an important lesson. This is why we have this class, and this is why this is an important topic in architecture. This is a problem that all architects have, right? How to deal with the sun. You may not have access to the software. You may not have access to the data in the way that you want it, or you may have a problem that no one's ever encountered before. And it's very important to have the ability to write small pieces of software that can get you through that impasse, right? Or that can help you talk to other pieces of software to basically keep you moving forward. And this is an increasingly vital skill for architects, for really people in a lot of fields, okay? And that's one of the reasons why this course is required. We're giving you some insight into how this process works, not because we expect you to, everyone to be doing this, but if you will, and you'll definitely be working with people in a firm that are going to be building things like this for you, and you're going to need to know how to talk to them. You're going to be talking to Stan or you're going to be talking to Jennifer or somebody, and you say, I need to track the sun, I don't have the software for it, I need to get the location of a point in the sky and its vector, how do I do that? And they'll sit down with you like you sit down with your partner, and you'll draft a little script to do this. Okay? So I'm going to take you through a little bit of my process for how I came up with this, for how this tool works. And again, you may find out later on that, like, you know, somebody already programmed it, but at that point in time, you needed it. You needed that right away. And so having this ability is really useful. All right, so this is I mean, it's a whole lot of sound and nonsense just for this little thing. But let me try to explain to you like how we end up with this system. This is going to be the basis for all the scripts I'm going to show you today. Okay. So what I've got here is I start off with a system. And I'll try to turn this on so you can see my process here. Oops. Okay. So I've got. Go back to my talk here. What I'm trying to recreate is if you study this geometry, what is that? What is that green line? What kind of shape is it? It's a what?
Arc.
It's an arc. That's right. Yeah, it's not a curve. It's an arc. If you get the difference, like a curve could be an arc, but a curve could be lots of other arbitrary things. It's an arc through the sky, right? It has a starting point and a middle point and an end point. It describes a path like along a radius. And if we know that it has those properties of an arc, then we know that what we're trying to do is we're trying to build a very specific kind of arc. Okay? And in fact, that's where I end up in the middle of my script. So I work my way backwards. Okay? So I ask myself, how do I find those 3 points? Okay? How do I find basically where the sun rises, where the sun's going to be at noon, and where the sun's going to be at the end of the day? And those are my 3 points for my arc. Okay? And that arc changes, right, depending upon the time of year. Well, the problem is that, and this is actually where this is not so computational. So if you look at it from above, we're looking at now what I'm trying to do is I'm trying to do this right now. Okay? And so there's an angle of where the sun starts on the left side, and there's an angle where it ends up on the right side, and there's an angle here in the flat side, right? And then in elevation or in section, however you want to think about it, there's an azimuth. There's an angle of rise, okay? And I can't get that in Grasshopper. Like there's no way. So what you can do though is I can go to a website, and I've actually got this here, sustainabledesign.com, sun angle. Hopefully my browser is going to work here. And I get these angles by going to this website. And there are a lot of websites that are actually like this, but so I can type in my zip code, and I use my house here, and it's going to set the latitude and longitude for me, okay? And then I can say, I can set the date, and I'll set today's date, because why not? And you can find elevation. You can find elevation in Google Maps, actually. So if you know where your site is, you can find out Google Maps and get this information lickety-split. Let's call it 15 meters, I guess. And it wants a time. Fine, I'll give it a time. There we go. And so this is actually going to give me the time of the sunrise, time of the sunset. It'll give me so the time I put in is noon, so it gives me the azimuth angle. It gives me all the information that I need, right? It tells me what those angles are. This is really handy because, remember, I want the angle and the azimuth of the sun at sunrise and sunset, so I can plug these numbers in and I can get those values. This takes just a few. You basically have to calculate 3 times. If this was really computational, like if I was doing this in my scripting class, in my advanced class, I would write a script that pulls this data from this web page directly into Grasshopper. Like I would never touch this thing. But I just wanted to show you guys, like, you're only going to do it for a few times a year. You're going to do it for the longest day of the year, shortest day of the year, and equinox, just to give you like a range, okay? Or if there's any specific day of the year that you want to plan for. But this is perfectly fine, right? Like, there's kind of a rule, and you guys, I'm not going to have this on a slide, so you might write this one down. But if you have to do something more than 3 times, then you probably want to write a script. Like, you want to find a way to like write a script, okay? Because it'll probably take you 3 times as long to like write the thing as it does to actually do it like 3 times by hand. Okay? If you're not going to do it more than that, then just go ahead and do it by hand. Okay? Because it's just not worth the investment. How do you know if you're going to do it more than 3 times? Well, that's something that takes a little bit of experience. But in this case, because of this, because it doesn't take me very long to calculate this, I didn't write the script for this. Okay? And I wanted to show you guys how this is possible. So I go in, and in this case, I had the date for, the date was like November 10th. I just put it in as an arbitrary date. I typed in the numbers for the time for sunrise. It gave me the azimuth. I typed in the time for noon and the time for the sunset, and you can see these are pretty close. And this is a number this is a positive and a negative, and that's a number that's pretty far between them. So that would give us the arc. Okay, like intuitively we understand that those are the. And what I did in order to do that, I just took a line and I rotated it by those numbers, and that's going to describe that. The length of the line is arbitrary. It doesn't have to be any set length, because if you understand how the sun works, the sun is really far away. Right? Like it takes 8 minutes for light to get here at light speed. It's like incredibly far away. Okay, all that and all that, because of that, all the rays that come from the sun are basically parallel to us. It doesn't matter like how high up we are or how far down we are. It's so far away from us that the rays are like parallel. So angle on Earth like doesn't really matter. It's just the distance between the Earth and the Earth is essentially a point, and the sun is a point, and there's just like a straight line between them. It's not like a bunch of points on Earth that have to talk to the sun. So because of that. I don't know if this makes sense, but the length of the line that I used to create this like diagram like doesn't really all matter that much, because all I'm trying to do, like I'm just essentially scaling it, is just find out what that angle is between the Earth and the sun, and then I'll use that to do my sun studies. Okay, but I just want, if in case you encounter that in the script, like that's actually not going to affect your measurement. All of this is just to get the angle. See, it's actually probably a little convoluted. Okay, so I've got the azimuth, which is the arc, like on in this plane, and then the altitude, which is how high up the sun is at noon. Like what's the angle of that to the base plane? The altitude at sunset and sunrise is 0, right? So because that's the horizon, more or less. Okay, and then once I do that, I extract the endpoints of those 3 lines, and I use those to build the arc. So now I have the arc of the sun for that particular day of the year. Okay? All that make sense? And it's kind of a lengthy explanation, but I want to give you guys a sense of like how I deconstruct a problem. This is one of the most difficult things to really like describe. I could just give this to you, but you get no insight into how you might actually do this, right? And it all comes from understanding that this is an arc. Like you work your way backwards. What's the information I'm missing? I don't know where the angles are. I don't know what the altitude is. Where can I get that information, right? Find it in a website. And then so these are now my inputs, and this is now my first output. Okay, so the other thing that I have to do is figure out where the sun is along that path. Like I've got the path of the sun. I got to know where the sun is, okay? Now, that's kind of tricky, because it's a length of time that like changes depending upon what day it is. So I can't just say like, if I want to know where the sun is at noon, that might be pretty easy, because maybe it's like 50% of the way along that line, right? I don't know what the length is, but I know what the percentage is. If I want to know if it's like 3 o'clock in the afternoon, you might say, oh, well then it's probably just like 75% or something like that. But that's not like mathematically correct, right? Because again, the length of the day changes. In the winter, that might be 60%. In the summer, that might be only like 55%, right? So it's actually just going to change depending upon the time of day. So one thing that I did was that I looked at the number of minutes in a day. So I just take like the length of the day, so sunset minus sunrise. Take it times 60, because 60 minutes in an hour, basically, right? And then what I did was I looked at the time that I was interested in. So in this case, it's like 1410, so 210. Multiply that times 60. I can figure out where that falls along that number of minutes, and that gives me a parameter for where the sun is along that curve. Does that make sense? So again, you have to be very precise about what kind of information you're trying to find. Like if you're really interested in what the angle is, you can't fudge it. You can't say, oh, I guess it's like this, because the system's changing. Okay, so we need something that's going to adapt whenever the system changes. And the way that I figured out to do that was just to turn it into, math, basically. So what I've got is sunrise and sunset, right? And that gives me a domain, it gives me a range. So this is from midnight, it's 413 minutes from midnight to 1,041 minutes from midnight, right? Because that's 0. We start counting from 0, okay? And that gives us our range. This is 0, this is 1, right, in terms of our parameter. And then I figure out 2:10 in the afternoon is 850 minutes after midnight. And I can use a tool like Remap to basically figure out that that's 0.69586 in the day, right? We're 69.5% through the day. And that is where the sun is, okay? So again, like this is not, I would not ask you guys to have to do something like this for me, but this is the kind of thing that people are doing every day, and this is the kind of thing that like you could have input on, And if you're interested in it, like we have other courses, we have a whole major that's devoted to solving these kinds of problems. So the kinds of things that you see online, even tools like Grasshopper, right? Somebody had to sit down and say like, how do I find the points along an arc? And they had to go bust out a geometry book, and they had to write the arc tool in the first place, so that you can just plug stuff into it, okay? And that's what I sort of did. Like, you can imagine this thing. Actually, I could probably make this into a component where you just plug in these numbers and you plug in the time of day and you get that point, okay? A lot of work, but once you've got it, you can use it to do lots of things. And so that's the basis of this script, okay? Any questions on the sunlight script? And this is yours. You can use it. You can do whatever you want with it, If you need this, I'm going to show you some stuff you can use in the studio today. But anyway, I hope that explanation makes some sense. Okay, so moving on. Hopefully, okay. So some of the things, some of you guys have already done these for your precedent study. We did some things with Louvers, right? Now, Louvers is a very simple idea. It's just like a shading device. And you can have static Louvers, which are essentially designed to accommodate a range of times. So that they're like, most of the time they are shading you from the sun. They may not work all the time. They may be shading you all the time, but then they get very deep, and that may affect the aesthetics of the space. This is a project that I think some of you guys had, like Telephonic headquarters. So there are Louvers embedded into the like window system here, right? So that's an idea of kind of a I call them like a dumb Louver, just because they don't have any like intelligence in them. Okay, and for the most part, that's what a lot of Louvers are. Now we also know that Louvers can be moved, though, right? And you can move them vertically, move them horizontally, depending upon what side of the building they're on. Okay. Typically, we want on the east-west sides of the buildings, we want Louvers to be moving like vertically, to be shading the sun. As the sun path like travels in the day, they're either moved by the occupants of the building or they're mechanically actuated. Okay, and then typically on the north-south sides of the building, we have horizontal Louvers and be moving up and down. Alex, am I right? Okay, I hope so. Otherwise, it's the opposite of that, right? There's only two choices. Okay, and then we get sort of more like dynamic kind of Louvers, right? We have these systems where we might be like folding the building or like tearing the building, and again, some of you guys have projects that were like this, right? So we can kind of completely enclose areas or completely expose areas, and then somewhere in between we have this kind of pivot that we see, here, okay? And this is made possible by flexible materials or digital fabrication, like that sort of thing. You can see that on a much larger scale. So you get this kind of fish gill kind of configuration with your aluminum skin. And again, I think we had a project that was like this semester that was faceted. Okay. So let's take a look at that. Some of you guys, I asked you to like vary your script from the precedent. And we discussed different ways of like modifying it and of getting it to behave differently. One of the missing pieces that I sort of talked about, and so some of you guys did this actually, was, you could make your thing actuate according to the position of the sun, but we didn't know how to do that. Okay, so if you were curious and you didn't get a chance to do that, this might help you make sense of that. Okay, so I need to open up my aperture model. Actually, that's not the wrong one. Let's just do, the Louvers model works on its own. Sorry, okay. So here we have a set of louvers. Whoa, there we go. So my script, all this is the script you just saw. And we have the sun. And then this is a series of louvers here. And basically the way that this works, the way my script works, again, is that I can change, hang on a second. Come on, there we go, okay. I have the sun, I have my thing, I can change the time of day, and you're going to see these things adjust. So you can see where the sun is at noon, and where the sun is as it goes later in the day. And actually, when it's no longer, around, the script doesn't work anymore because it can't find that other point. All right, but we need that to keep the script consistent. And so you can see, like, as the time of day changes, these are going to rotate, open and closed. Okay, and we could make them oscillate a little bit differently. But so how does that work? So we know that we get the sun angle. We know that we have like the angle between the point and the sun. Okay, and that point could basically just be anywhere that's in the center of this object. Okay, and actually, let me take a little detour here. So we've done some things, and one of the questions that was on the test was, which of the transforms uses a vector, and we said that move was a vector. Okay, and you guys might remember from math class like what a vector is. Okay, so we know what's a vector. Let me describe a vector to me. What does it have? Like, what are its properties?
It has length and direction.
Yeah, perfect. It has length and direction. So it's a point in space, and it's basically like, you can imagine it as like a ray, because it can go on, just infinitely, or it can have a certain amplitude, but it's heading towards something with some kind of magnitude, and that's essentially what we use to move things. Okay. And so the simplest way to define a vector is through 2 points. So if I make a point, and I make point, so I'm going to go ahead and reference that. There's actually a vector from 2 points. So A and B will produce a vector. Now, you don't actually see the vectors, and that's why we have a whole vector tab, actually, but you can do a vector display, and I may have shown this to you before on the video, but so you can say the anchor point is whatever point you want to use to start drawing the anchor. I'm going to use this bottom point, and then the V is the. And what actually ends up happening is, because I drew it from A to B, that's the direction that it's drawing from. So that matters. Like which point's first, which point's second matters in the direction of it. But you saw, like, when I did it in the opposite thing, it's still the same angle, right? It's just going in a different direction. And the amplitude in this case is just the distance between these 2 points. But you'll note, it's parametric. So if I move it around, it's going to be pointing. And if I have that, I can do something like, I can take a first vector and a second vector and find the angle between them. Okay, and the base vector, could just be the z-plane. Actually, the x-plane. What am I thinking about? Because remember, x, y, and z were the vectors that we were using to move things, and they're kind of dumb vectors too. Like they don't have anything. They're just kind of 0, 90, and 0 in this direction, right? They're just kind of flat. But what that does is, if I measure the difference between our new vector that I made and the world, it gives me the angle in radians. Okay, and that's the key to all the stuff we're going to be doing. Okay, we measure the angle between the ground, which we take to be flat, and the sun, which we take to be some other angle, and that is a number that we can use to drive the transformations. Okay, so in the same way that we had the distance between a point and other points as the driver in our attractor scripts, we're going to use the angle between the sun and some point on our object as that driver. Okay, and that does rotation. That will do transformation to allow things to open or close, and that's going to prevent sunlight from entering in our spaces, or it's going to allow sunlight to enter our spaces. I'll show you some examples of architecture that wants light to be in a specific location at a specific time. Like in a church, like on a holy day, it's going to drop light like right down on the altar. Okay, how do they do that, right? You could do it with graph paper and a side rule or whatever. We can do it parametrically, all right? It's kind of a joke, but yeah. It's a very good way to do it. So the idea of this is to look at the angle between the louver and the sun and to decide how open we want it, how closed we want it. Ostensibly, when the sun is directly perpendicular, right, to that, we want that thing closed. And as the sun moves away, we want to begin to open it to let in indirect light. So let's go back to our script and take a look at how this actually works. So basically, I draw some rectangles, and that's really what this is to begin with. So you can see they got rectangles here that I then sweep and cap, so I make a solid. Not a big deal. Okay. Then I move them in a series. This old hat for us. We can change the number of louvers parametrically. We can change the spacing between them. Then the magic happens, right? So we take our sun's point, which is B, which is all the way like over the, well, then your distance the other side. Plug that into a point. In this case, it's just a point that I'm using that's in the center of this thing, because I'm not interested in the individual characteristics, because they're all going to rotate the same way. I use that to get the vector. I did the same thing here. I find the distance. I find the angle, and then I use the angle in a rotate 3D. And the distance. I've talked to some of you guys about this. We've done rotate. The only difference between that and rotate 3D. So rotate rotates around a point. Rotate 3D is like a hinge. So you can say that like one side is the hinge, and everything, and it's going to rotate along that piece, right? So if this is the hinge, it's going to rotate. So that is really useful because it's a lot of the ways we rotate things. You don't want it to rotate like a record or a pizza.
So do you have to do a sweep and not a loft so that you have that hinge piece?
Oh no, not at all. And in fact, this could just be a plane. It doesn't have to be solid at all. I just like them solid.
So how do you set the hinge?
What's that?
How do you set the hinge?
The hinge in this case, good question. The hinge in this case is actually, I just made it the x-axis. You can make it anything that's a linear piece or like a vector. So I could take this point and that point and call it the hinge, or this point and that point of the object and call it a hinge.
So would you have to like evaluate your form? Like
You can do that, yeah.
How would you find an edge of that rectangle to use it as the hinge?
Okay, so if it's the rectangle, I could take the form that I created. I could do a BREC explode. I could get into the data structure, find out what that point is and what the other counterpoint is, draw a line with them, and then plug that in for my axis. Conversely, if I wanted to rotate it for whatever reason this way, I would just find these 2 points. All I need to do is draw a line. If you can extract a line from your form, you've got an axis. Yeah, that's a great question. Yeah, I'm sorry, I didn't mean to go through that. So yeah, and it doesn't have to be a rectangle. It could be some form that you create, as long as you can find a way to find that axis somewhere. Even if you just make it arbitrary, that's how it's going to work. Okay, does that explanation make sense for finding the axis? Okay, it's easy if it's a surface, right? Because then you can just take the edge too. If it's not even, you can take the edge of it, use it as a rectangle, and then you can extrude it to create a solid.
Yeah.
It doesn't really matter. It's just a matter of, different ways to end up with the same result.
But you do want to be able to control it.
Oh, you do. But I think in the end, they're both going to be solids. They're both going to be rotated. So the difference is really kind of negligible. Okay. So again, this is just saying that in this case, as the sun gets higher, these things are going to close because it doesn't want to let light into the building. Okay. It's a very simple relationship. Let's take a look at another example. So I got these I call these warped louvers. I don't think that's a specific architectural term, but I think we know these when we see them. And they're kind of like the skin thing I just showed you. So if I take the time of day and I move the sun, you can see that these are actually adapting, again, to sort of block the light. It's really, the twist is really happening like up here, and I'm keeping this bottom open for whatever reason. Maybe I want to like illuminate a hallway or some kind of circulation space with indirect light, so I'm going to bounce that light into the space. But I want to keep the light out of people's eyes, and so I'm twisting them at a taller height. Okay, and so this is how the script is basically going through the day, and it's going to, as the sun moves, going to present that face to the sun. And this script, I have the ability, so I can change the location of that twist element. If I was going to get really fancy, I could parametrically adjust the position of each twist according to some curve or something like that, right? To be really tricky with it. But in this case, they're basically all the same, and there's some kind of mechanical thing that's actually twisting that center frame. And this goes back to the Louvre pattern that I showed you earlier, where it's just 3 rectangles and then the one in the middle twists. But now, what's twisting the middle one is the angle of the sun. Okay? And there's various ways to do this one as well. So in a short, it's almost like the last one where, you know, this is a line. So I take this line that I've created, and I'm finding different positions along that line to distribute my rectangle. And then I'm basically taking one. I've rotated, so this one is 0 degrees, this one's 90 degrees, and this middle one is some other like amount. This is another rotate 3D, so I'm rotating along that axis, which is this line. Okay, so that's another reason for that too. I want it to rotate as if it's on a pole between those two cross sections. And then I graphed them together, and these are lofted. So I like solids because this is the kind of stuff that, you know, renders correctly. It's going to fabricate for you. If it's schematic, there's no reason why you can't just present these as surfaces. But I do want you guys to be thinking about how to get them into solids because it's going to matter later. Okay, you're not going to be able to do more sophisticated stuff unless this is like airtight geometry. And we haven't really talked about digifab yet, but that's going to become pretty important. So, okay. So louvers. Any questions on the two types of louvers? You can do an unwarped louver, like a dumb, louver, just by rotating the whole thing. Okay, you don't have to rotate the 3 things separately. You just take the whole thing and rotate it on that plane. Okay, so it's pretty easy to make that kind of variation. Okay, the other type of like sunlight adaptation I want to talk about are what I call apertures or openings. It's a really famous project by Jean Nouvel, the Arab Institute in Paris. It's famous because it's kind of beautiful. It's also famous because it doesn't work so well anymore. This is one of these early experiments in actuated surfaces. You're seeing a lot of kinetic facades. This is the kind of stuff that I think Chinese Studio is doing. This is kind of an early example of it. It's really quite gorgeous. What it is that it's these really intricate mechanical shutters, like the shutters on a camera. And there actually are sensors, and depending upon the amount of sunlight or if someone wants to change it, these things all kind of iris shut. Well, maybe at the time it seemed like a great idea, but these things, there's so many points of articulation. They probably have to be maintained, and there's tons of them. And they just stopped working, basically. So a few of them do, but it's not. Some of them are stuck open, some of them are stuck shut. It's kind of an interesting facade. Anyway, it's beautiful. It's based on these these sort of Islamic patterns. This is kind of how it looks in the space. It's this very kind of 80s kind of what do you want to call it? This sort of industrial techie kind of architecture with this sort of exposed structure and chrome, and then it has this facade. It's kind of like RoboCop or something, the old RoboCop. And anyway, but this is just an example. This is an aperture. This is like almost like our like attractors, right? You just have something that has a radius that changes. But in this case, the radius that's changing is changing because of like whether the sun is perpendicular to it or not, right? Shutters are closed when the sun is, pointed at you, and they're open when it's not, giving you indirect light. Salk Institute. Okay, it's totally not a articulated project in the sense that it's not automated or mechanical. But if you guys know from this project, there are these teak wood like shutters that can be manipulated into different kinds of like positions depending upon if someone in the lab or in these offices wants more or less light. And this is an idea, so again, it can be done like manually or it can be done, like automatically. This is a really famous example. So this is just showing the different kinds of like configurations that are actually possible with these. So you can see, and then these pieces actually open and close too. Okay, let's take a look at some scripts for that as well. Okay. This script is going to take surface. And I have to say, this one doesn't work. I need to revise this one. It doesn't work as well as I would like it to, but it's a proof of concept. So I'm going to reference that surface. Oh no, this one works okay. Okay, this is one of them is not happy. Okay, so if you look at the script, we go back, and as I do, if I change the position of the sun, can you guys see that? The difference? So you can see the openings here, and these are not as open when the sun passes through. So as the sun gets perpendicular to it, so it's basically like an attractor, but the attractor is the sun. Okay, and this would work for any arbitrary, like building. You could have lots of curves. This is like flat for right now. I am actually interested in the angle of each individual panel to the sun because I kind of want. In this case, I am interested in measuring that. So it's not like a louver. It has to be much more specific. So if we had this as a building, there'd be like a bright spot, like right where the specularity of the sun hits the building, and these things would like pucker closed. Okay. So you can take a look at the script. The way it works is, you can see the geometry. It's kind of strange. I have a surface that I subdivide, and I place a circle on the inside of it, and I basically loft it from the edge of the frame to the circle. Okay. And then as it opens and closes the loft, it just reforms the loft. It's kind of a slow script because of that. I think if you had a faster computer, it'd probably work. But basically, we just end up with a series of lofts. Okay, so you guys can take a look at this script. There's a little bit of magic in it because we're going from a rectangle to a circle, and the way that the points connect has to be massaged a little bit. But that's kind of technical. I'll let you guys see that. But okay, let's take a look at another one of these here. Aperture V2. This might be the one that... Actually, this one's okay too. Okay, so let's reference the script again. Surface. And this is the one, I think some students had a project that was kind of like this, not the exact geometry, but it's this idea of this is almost kind of a Salk Institute where the windows can kind of open and close a bit. They're kind of on these like shutters. And so what this script does is as the sun's path moves, the shutters, they're just simple like rectangles. They're almost kind of like garage doors, they're kind of rolling garage doors. They either stay up or they like roll down. Okay. And the way that this script works is that, first of all, and this is really handy, I take the lofted surface and I scale it down a little bit, and then I loft those two together, and it gives me the frame to get a frame. Okay. Then what I did was I extracted that line from the inner frame, and then I moved it by some amount depending upon the angle of the sun, and I loft those two together. That's it. Okay, so it's pretty straightforward. So again, this is coming back to the stuff I talked about on midterm and what we just talked about in the question that was just asked. It's so critical to know how to get what you want and then how to know how to extract those parts, right? I want a surface, I got lines, how do I get that line? And then how do I get this other line to be smart? And now I've got a smart surface. Okay? And that's what this one is. And you can make this much more complicated than this, but it's a very straightforward principle. And it kind of creates an interesting aesthetic. So you might have, there's a series of sensors on each window, and the idea of this is that it rolls this shading device up or down. There's lots of different like design options that you can apply to that, but that's kind of how this is. And you get kind of a diagram of the sun's path on the outside of your building. Okay? Okay. Any questions about that system, about apertures? Okay. Now, I've been doing a lot of facades, but you could also think of them as skylights as well, right? You can measure, you could have a flat surface, and you could look at the angle between that and where the sun is, and you could choose to like operate some kind of a sunshade or some kind of a skylight-like device. Okay, light shelves. This is one I'm not going to specifically cover, but it is a daylighting tool. A light shelf is basically what you see here, this kind of rectangular piece. And what it does is it prevents direct light from getting into this space, but it increases the overall like ambient light of the space by bouncing the light off of the ceiling. Okay, so it serves a dual function. These are not parametric. Like they're not. You're not going to see ones that kind of shoot in and out. Like they don't do that. I don't know. Maybe we could design one that does, but there's no reason to do that. The reason why I bring it up parametrically is because in order to study how this works, you could create a diagrammatic like light shelf, right? And you could even use, because the light basically kind of works like a laser, right? It's going to bounce. There are some things you can do in Grasshopper that you could look at the vector. You can change the angle of the vector as it hits a surface to be its like opposite, and you can essentially create a parametric version of that diagram to study where your light shelf needs to be. Like, where does the light need to go and where does it not need to go? Well, I could fudge it, or I could build 10 models and I could take them down to Dale's thing, or I could make a parametric model of it in order to understand it. Then I build one model and it's probably going to be really close. I can take it down to Dale's and I can really study it, or I can simulate it in the computer, right? Then I'm probably only making 2 models as opposed to the number that I would need to study it in the lab. Okay, so you can do parametric diagrams as well, right? Because again, there's a little bit of math in this in the way that we study those rays, and I'll put up an example of that later. There's also a kind of like another idea of like the sun shade, which is kind of like a louver, and the way that you want to change the path of light as it enters into your building. You could study these as well with a similar method. Some of them are depending upon the side of the building, if you have like a corner of a building that's kind of, oriented in, let's say, this is like a southeast corner, you might need shading devices that are both vertical and horizontal. Okay, you guys will learn more about this later, but being able to study, so there's actually like an exterior shading device and an interior light shelf in this design. So you can actually like combine these systems to affect the sunlight in your building. Okay. The last type I want to talk about are called light cannons or skylights, and I believe we've all been exposed to light cannons, at least my third years have, in the La Tourette study. Remember like Corbusier's? He's a big fan of light cannons. You don't see enough of them. So yeah, in La Tourette, we have particularly, these are kind of the more famous ones. It's a big one. Actually, it's a bell tower. But they're angled a specific way. They're painted a certain color. Remember we talked about in the rendering lecture that when light bounces off a colored surface, it like paints light on other things. That's exactly what Corbu was doing without the benefit of V-Ray. And that's essentially how he takes these like light guns and positions them over his over the altars in this chapel. It's a bad picture, but you can see the difference between the interior of the chapel and the space with the light guns at the right time of day, at the right time of year. Like that's a really dramatic space. Okay, and he's basically got the math textbook out and like figured out what that angle needed to be. You can have a website. Another study. There's some other light guns here as well. So for example, and I think this is the rectory, I'm not sure, but so for example, in the morning, they may want to bring light in because you're trying to wake up, you're groggy, you're a monk, you haven't had your coffee yet. And so like as you're changing in your vestments, like Corbu is really interested in bringing in direct light, okay? And this kind of godly light from above, not light from the sides, right? Light from like right above your head. Okay, so a very specific implementation of that. You can see here. So again, they're like bouncing light off surfaces. This is a new Corbu, not a new one, but recently completed. It is like Corbusier design, really stunning. Saint Pierre. I encourage you guys to, if you haven't like looked into it or like read about it, I would really check it out. It's a really beautiful. And this is kind of again with the light cannons, very specific, implementation, like where he wants the light to go. You can see that they're kind of similarly, colored. They're just like modern architectural technology applied to Corbusier design is really striking. You can see here the surface of the shelf here painted a color to kind of cast different colors. Is green, blue. Pretty amazing space. This is a community center. I think it's in Germany. And there's a daycare that's below grade. And so to bring in daylight, they actually have these light cannons angled as well. And they're also painted. So it's not just churches. There's other uses for these things as well. And it's not just Corbu. He doesn't have the patent on them. This is the Dali Museum by HOK. And in this case, this is really interesting actually. You think in museums you don't want to bring in direct light. And I would even try to avoid light as much as you can on a painting, but here they specifically want to eliminate this, like with a light gun. It's indirect, but I need to read more about this. But so here's an application in a museum of actually trying to bring in light. There's another church, St. Bride's. It's really famous, kind of modern, church, bringing in these light guns. I forgot the name of this one. It'll come to me. This is Peter Cook. Oh, Kunst das Gras. There, thanks for putting the label on there, Nick. Okay, so this is obviously more of this kind of late '90s blobitecture, and there are these light guns that kind of ooze out of the surface like a sea urchin. But these are specifically designed. You can see them in the computer here. So not only is it the angle, but it's also like the way that they open up inside the space. They did a lot of diagrammatic models to actually study this. And they're bringing in daylight into the space, right, to save money. And then they have these like tubes that are actually inside of it, so that when it is dark, they can turn on these lights on the inside to like illuminate the space. So they actually do double duty. They're skylights and they're interior lights. Peter Cook. Okay, let's take a quick look at that script, and then I'll send you guys packing. Okay, so light guns, and this is the one. It's a bad finale to end on because it doesn't quite look as good as I'd like it to. All right. So this is one example of light guns, and what I've got is two rectangles that are lofted, and if you look at it, they're kind of they're angled towards the sun in this case, and they project like out of the building. They're kind of twisted, which I don't care for. I'll make them bigger. The issue is the way that I created them. There's some, like the angle is, you can see the kind of tyranny twisting is happening. I need to revise this, but you start with a subdivided surface again, you scale it, you create a vector from the inside of that surface to the sun, and you point it at the sun. Use that to move the copy, and then you loft the two together, and that presents a light gun. Now, your surface is not going to do this, right? Like, it's not going to move itself. What you're going to do is you're going to find a time of day or time of year to fix those light guns, right? Or you do a PhD on how to actually make this thing actually actuate. There's probably some way to do it. But this is kind of getting, the other designs I've shown you, none of those are movable, right? They're like a fixed thing. But the principle is that, again, you find that angle and you use that to kind of create this lofted form. This could be a tube, it could be a polygon, it could be a square, it could be any kind of arbitrary kind of shape. But the idea is that the angle between this and this, right, is this vector that's along that line. So again, extending this idea, well, two big ideas. One, if you don't have something, you're empowered to make it by computation. Like if the tool doesn't exist, or the software is too expensive, or you can't find it, or it's in the wrong language, or you just have an idea that no one's ever done yet, you write your own script. Okay, you can do the research, you can talk to computer scientists, you can figure out how to get around that kind of roadblock. Second is this extension of this idea that we learned when we did the attractors last time, which is that all we're doing in these two instances is a very simple algorithm, is we're just looking at the conditions between one thing and another thing and using that to drive a form. Okay? And the meaning that we ascribe each of those, right, that's the really interesting part, is what kinds of relationships are we trying to create, what do those mean, and what are the forms that we get out of those things. And that's the kind of stuff that we really talk about more in our design studios, and we talk about with our colleagues. But from a technical standpoint, we've looked at distance as a driver, and what are the different things we get from that. And now we've seen vector as a driver, right? We've seen how we can do angle. There's probably a way to combine both, okay, right? To be able to see that mathematically. And we're going to be seeing later on in this unit ways of essentially looking at these as logical tests. So right now it's been basically like a number, but we can say is the thing parallel or not? Yes or no, right? Is the angle greater than this or less than that? Yes or no? And we can use that to begin to drive automated testing of these solutions for us by the computer. So we're not scrubbing here to find the optimal time. The computer is doing the calculations for us, and it's going to give us an analysis of what that optimal time is. You might want to use to bring the most amount of light into a space with the least amount of material. The computer can help you figure that out. Okay? But it begins by understanding how to do that test in the first place. And that's what the point of today is. Okay? If you guys have questions about how to get daylighting analysis into your projects, or skylight analysis, I can actually talk to you about that. But these scripts are going to be posted online. Feel free to modify them. But always, if you have questions about your studio stuff you want to do with this, let me know. I'll talk to you about it. That's it. I'll see you guys later.